Article 685.10 of the National Electrical Code states that a service disconnecting means must be installed for wells and pumps. Section 685.10 specifies that the disconnecting means must be located in a readily accessible location outside the well. Section 685.10 allows the use of a lockout device at the disconnecting means to prevent operation of the well or pump during servicing or maintenance. The NEC does not specifically require a lockout on the dishwasher breaker. However, local electrical codes may have additional requirements. Section 422.56 of the NEC does require that dishwashers have a disconnect switch readily accessible to the operator. A lockout device can be used to supplement this disconnect switch, providing an additional layer of safety. The NEC is a minimum requirement, and local codes may have additional or more stringent requirements. It is always advisable to consult with the local electrical inspector for specific code requirements. A service disconnecting means is a device used to disconnect all current carrying conductors of a circuit from the source of supply. This ensures that the circuit is de-energized, providing a safe environment for maintenance or repair work. The disconnecting means for a well or pump must be located in a readily accessible location outside the well. This ensures that the disconnecting means is easily accessible in case of an emergency or for routine maintenance. The location outside the well also prevents the disconnecting means from being exposed to the harsh conditions inside the well. A lockout device is a device used to prevent the operation of a well or pump during servicing or maintenance. The lockout device is typically a physical barrier that prevents the disconnecting means from being switched on. This ensures that the well or pump cannot be accidentally turned on while someone is working on it. The NEC does not specifically require a lockout on the dishwasher breaker, but local electrical codes may have additional requirements. These additional requirements may be due to local safety concerns or to align with specific industry practices. It is important to check with the local electrical inspector to determine if there are any additional requirements for dishwasher breakers in your area. Section 422.56 of the NEC requires that dishwashers have a disconnect switch readily accessible to the operator. This disconnect switch allows the operator to quickly de-energize the dishwasher in case of an emergency or for routine maintenance. The disconnect switch must be readily accessible, meaning that it must be easily accessible without the use of tools or special equipment. A lockout device can be used to supplement this disconnect switch, providing an additional layer of safety. The lockout device can prevent the dishwasher from being accidentally turned on while someone is working on it. This is particularly important in commercial kitchens where multiple people may be working in the same area. The NEC is a minimum requirement, and local codes may have additional or more stringent requirements. This means that the local electrical codes may require more than what is specified in the NEC. It is always advisable to consult with the local electrical inspector for specific code requirements. The local electrical inspector is responsible for enforcing the electrical codes in your area. They can provide you with information on the specific code requirements that apply to your project. They can also help you to ensure that your electrical work is safe and compliant with the code. Here are some additional points to consider regarding well pump and dishwasher breaker lockouts. Firstly, the specific requirements for well pump and dishwasher breaker lockouts may vary depending on the jurisdiction. It is important to check with the local electrical inspector to determine the specific requirements in your area. Secondly, lockout devices should be properly installed and maintained to ensure that they function correctly. The lockout device should be able to withstand the environmental conditions in which it is installed. Thirdly, lockout procedures should be followed whenever servicing or maintaining a well pump or dishwasher. The lockout procedure should include verifying that the equipment is de-energized before starting work. Fourthly, electrical safety training should be provided to all personnel who may be servicing or maintaining well pumps or dishwashers. The training should cover the hazards of electricity and the proper procedures for working safely with electrical equipment. Fifthly, regular inspections should be conducted to ensure that lockout devices are in good working condition and that lockout procedures are being followed. The inspection should be conducted by a qualified person. Sixthly, documentation should be maintained of all lockout procedures, training, and inspections. The documentation should be readily available for review. Seventhly, it is important to understand the difference between a disconnect switch and a lockout device. A disconnect switch is used to de-energize equipment for routine maintenance or in an emergency. A lockout device is used to prevent equipment from being accidentally turned on during servicing or maintenance. Eighthly, the location of the disconnect switch should be clearly marked. The marking should be visible and easily understood. Ninthly, the disconnect switch should be readily accessible. It should not be obstructed by equipment or other objects. Tenthly, the disconnect switch should be properly sized for the equipment it is serving. The size of the disconnect switch should be based on the electrical load of the equipment. Here are some additional details regarding Article 685.10 of the NEC, which pertains to integrated electrical systems, which could include well pumps. This article addresses installations where orderly shutdown is required to minimize the risk to personnel and equipment. 685.10 requires that disconnecting means must be grouped. For integrated electrical systems, the disconnecting means for each circuit must be grouped and identified as parts of the integrated system. This facilitates a coordinated and orderly shutdown. 685.10 dictates accessibility and location. The disconnecting means must be readily accessible and located at a place where qualified persons can perform the necessary procedures. This is important for safety and efficiency during maintenance and emergency situations. 685.10 concerns the type of disconnection. Each disconnecting means must be capable of disconnecting all ungrounded conductors of the circuit simultaneously. This ensures complete isolation of the circuit. Regarding dishwashers and Section 422.56 of the NEC, which addresses disconnection of appliances. 422.56 are for cord and plug connected dishwashers. A separable connector or an attachment plug and receptacle is permitted to serve as the disconnecting means. This means the act of unplugging the dishwasher can be considered the disconnect. 422.56b addresses the location of the disconnecting means. The disconnecting means must be readily accessible and located within sight from the appliance or be capable of being locked in the open position. This ensures the operator can easily disconnect power and prevent accidental re-energization during service. For permanently connected dishwashers, a switch or circuit breaker can serve as the disconnecting means. However, it must meet the requirements of being readily accessible and lockable. In summary, for well pumps, the NEC emphasizes a readily accessible disconnecting means located outside the well, often with provisions for lockout during maintenance. For dishwashers, the NEC requires a readily accessible disconnecting means, which can be a plug and receptacle for cord-connected units, or a switch or breaker for hardwired units. The option for a lockout is often available to enhance safety during servicing. Local codes can impose more stringent requirements. Always consult the local electrical inspector. The NEC serves as the cornerstone for electrical safety. Here are some key concepts. The scope of the NEC is to provide a standardized set of rules and guidelines for electrical installations. It's not a design manual, but a safety standard. It aims to safeguard persons and property from hazards arising from the use of electricity. The NEC is updated every 3 years to incorporate new technologies, address emerging safety concerns, and refine existing rules based on field experience and expert input. This ensures the code remains relevant and effective. Enforcement of the NEC is typically the responsibility of local jurisdictions such as cities, counties, or states. These jurisdictions adopt the NEC as law and employ electrical inspectors to verify compliance with the code. The structure of the NEC is organized into chapters, articles, and sections. Chapters cover broad topics, such as wiring and protection, equipment for general use, and special occupancies. Articles delve into specific aspects of these topics, while sections provide detailed requirements. Some common chapters are Chapter 1. General. This chapter covers definitions, general requirements for electrical installations, and rules for examination, installation, and use of equipment. Chapter 2. Wiring and protection. This chapter addresses wiring methods, overcurrent protection, grounding, and bonding. Chapter 3. Wiring methods and materials. This chapter covers the types of wiring methods permitted, such as cables, conduits, and raceways, and the materials used in electrical installations. Chapter 4. Equipment for general use. This chapter covers the installation and use of electrical equipment such as receptacles, switches, lighting fixtures, and appliances. Chapter 5. Special occupancies. This chapter covers installations and special occupancies such as hazardous locations, healthcare facilities, and swimming pools. Some key articles are Article 100. Definitions. This article defines terms used throughout the NEC, ensuring consistent interpretation. Article 250. Grounding and bonding. This article covers the requirements for grounding and bonding electrical systems to provide a safe path for fault current. Article 300. Wiring methods. This article covers the general requirements for wiring methods such as support, protection, and installation. Article 400. Flexible cords and cables. This article covers the use of flexible cords and cables, including their permitted applications and limitations. Article 430. Motors, motor circuits, and controllers. This article covers the installation and protection of motors and motor circuits, including overcurrent protection, disconnecting means, and control equipment. Understanding the NEC involves a combination of studying the code book, attending training courses, and gaining practical experience. It is essential to stay up to date with the latest edition of the NEC and any local amendments. The NEC also contains informational annexes that provide additional guidance and explanations. These annexes are not part of the enforceable requirements of the code, but can be helpful in understanding the intent and application of the rules. It's also important to distinguish between mandatory rules, which use the word shall, and permissive rules, which use the word may. Mandatory rules must be followed, while permissive rules are allowed but not required. The NEC requires electrical plans to be submitted for review and approval before any electrical work is performed. This allows the electrical inspector to verify that the proposed installation complies with the code. The electrical inspections are conducted at various stages of the construction process to ensure that the work is being performed correctly and in accordance with the approved plans. The electrical inspector will typically conduct a rough-in inspection before the wiring is concealed and a final inspection after the installation is complete. If the electrical installation does not comply with the NEC, the electrical inspector will issue a correction notice listing the violations that must be corrected. The electrical work must be corrected and re-inspected before the electrical system can be energized. Working with electricity can be dangerous, and it is essential to take precautions to protect yourself from electrical shock and other hazards. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Here is some more information on grounding and bonding. Grounding and bonding are critical for electrical safety, providing a low impedance path for fault current to return to the source, thereby tripping the overcurrent protected device circuit breaker or fuse and de-energizing the circuit. Grounding refers to connecting the electrical system to the earth, typically through a grounding electrode, such as a ground rod or a metal water pipe. This provides a reference point for the electrical system and helps to stabilize voltage. Bonding refers to connecting all metal parts of the electrical system together, such as metal conduits, metal enclosures, and equipment grounding conductors. This creates a low impedance path for fault current and helps to prevent electrical shock hazards. The equipment grounding conductor EGC is a critical component of the grounding system. It is a conductor that connects the metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault current and helps to protect against electrical shock hazards. The size of the EGC is determined by the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of the EGC based on the rating of the overcurrent protective device. Grand fault circuit interrupters (GFCIs) are life-saving devices that protect against electrical shock hazards. GFCIs monitor the current flowing in the circuit and compare it to the current returning. If there is a difference of 5 mA or more, the GFCI will trip, de-energizing the circuit and preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Arc fault circuit interrupters (FSIs) are devices that protect against electrical fires caused by arcing faults. Arcing faults occur when electricity jumps from one conductor to another, creating a high-temperature arc that can ignite nearby combustible materials. FSIs detect arcing faults and trip, de-energizing the circuit and preventing a fire. FSIs are required in many locations, such as bedrooms, living rooms, and dining rooms, where there is a high risk of electrical fires. Here's some additional information on overcurrent protection. Overcurrent protection is essential for preventing damage to electrical equipment and wiring due to excessive current flow. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. Circuit breakers are reusable overcurrent protective devices that trip when an overcurrent occurs. They can be reset after the fault has been cleared. Fuses are one-time overcurrent protective devices that melt when an overcurrent occurs. They must be replaced after they have blown. The size of the overcurrent protective device is determined by the ampacity of the conductors it is protecting. The NEC provides tables that specify the maximum size of the overcurrent protective device based on the ampacity of the conductors. Short-circuit protection is designed to protect against high-magnitude, short-duration overcurrents that occur when there is a short circuit between two conductors. Short-circuit protective devices must be capable of interrupting the fault current without being damaged. Overload protection is designed to protect against low-magnitude, long-duration overcurrents that occur when equipment is overloaded. Overload protective devices must be capable of interrupting the overcurrent before it causes damage to the equipment or wiring. Selective coordination is a design practice that ensures that the overcurrent protective devices closest to the fault will trip first, minimizing the impact of the fault on the rest of the electrical system. Selective coordination is particularly important in critical applications such as hospitals and data centers, where it is essential to maintain power to essential equipment. Here's some additional information on wiring methods. Wiring methods refer to the types of conductors and raceways used in electrical installations. The NEC specifies the permitted wiring methods for various applications. Non-metallic sheath cable type NM is a common wiring method used in residential construction. It consists of two or more insulated conductors enclosed in a non-metallic sheath. Type NM cable is permitted in dry locations where it is not exposed to physical damage. Electrical metallic tubing ENT is a metallic raceway used to protect conductors. ENT is permitted in both concealed and exposed locations. Rigid metal conduit RMC is a heavy-duty metallic raceway used to protect conductors in harsh environments. RMC is permitted in both concealed and exposed locations. Liquid-tight flexible metal conduit LFMC is a flexible metallic raceway used to protect conductors in wet locations. LFMC is permitted in both concealed and exposed locations. Cable trays are open support systems used to support conductors in industrial and commercial applications. Cable trays are permitted in both concealed and exposed locations. The ampacity of conductors is the maximum amount of current that a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables that specify the ampacity of conductors based on their size, insulation type, and installation conditions. The de-rating of conductors is required when multiple conductors are installed in the same raceway or cable. The de-rating factors are specified in the NEC and are based on the number of conductors and the ambient temperature. The voltage drop in conductors is the reduction in voltage that occurs as current flows through the conductors. The NEC recommends limiting the voltage drop to 3% for branch circuits and 5% for feeders.